Nature of sound waves. In this section, we will study the nature and characteristics of sound waves. It is also important to deduce if sound travels with the same speed in different media. In the previous topic, we learnt that vibrating objects produce sound. We acknowledge sound through our ears. Sound needs a medium to travel. It cannot travel in vacuum. What comes to your mind when you hear the word wave? The first thing that comes to our mind would be lakes, rivers, ponds, or oceans. Isn't it amazing to watch the water drops create ripples? It is a phenomenal experience to watch in the rainy season. The waves are created by some form of a disturbance, such as a drop of water falling into the lake, a duck shaking its tail in the water, or a boat moving through the water. The waves are categorized as longitudinal and transverse waves. Click on the buttons to view respective information. A longitudinal wave is a wave in which the particles of the medium are displaced in a direction parallel to the direction of energy transport. A longitudinal wave can be created in a slinky if the slinky is stretched out horizontally and the end coil is vibrated back and forth in a horizontal direction. Because the coils of the slinky are vibrating longitudinally, there are regions where they become pressed together and other regions where they are spread apart. A region where the coils are pressed together in a small amount of space is known as a compression. A compression is a point on a medium through which a longitudinal wave is traveling which has the maximum density. A region where the coils are spread apart, thus maximizing the distance between coils, is known as a rarefaction. A rarefaction is a point on a medium through which a longitudinal wave is traveling which has the minimum density. A transverse wave is a wave in which the particles of the medium are displaced in a direction perpendicular to the direction of propagation. A transverse wave can be created in a rope if the rope is stretched out horizontally and the end is vibrated back and forth in a vertical direction. The dashed line drawn through the center of the diagram represents the equilibrium or rest position of the string. This is the position that the string would assume if there were no disturbance moving through it. Once a disturbance is introduced into the string, the particles of the string begin to vibrate upwards and downwards. At any given moment in time, a particle on the medium could be above or below the rest position. The crest of a wave is the point on the medium which exhibits the maximum amount of positive or upwards displacement from the rest position. Points A and F on the diagram represents the crests of this wave. The trough of a wave is the point on the medium which exhibits the maximum amount of negative or downwards displacement from the rest position. Points D and I on the diagram represent the troughs of this wave. To learn more about the characteristics of waves, click on the buttons to view information. The amplitude of a wave refers to the maximum amount of displacement of a particle on the medium from its rest position. In a sense, the amplitude is the distance from rest to crest. Similarly, the amplitude can be measured from the rest position to the trough position. The wavelength of a wave is simply the length of one complete wave cycle. A wave has a repeating pattern, and the length of one such repetition, known as a wave cycle, is the wavelength. The wavelength can be measured as the distance from crest to crest or from trough to trough. In fact, the wavelength of a wave can be measured as the distance from a point on a wave to the corresponding point on the next cycle of the wave. In the diagram above, the wavelength is the distance from A to E, or the distance from B to G, or the distance from E to J, or the distance from D to I, or the distance from C to H. Any one of these distance measurements would suffice in determining the wavelength of this wave. The distance between two consecutive compressions, C, or two consecutive rarefactions, is called the wavelength. The wavelength is usually represented by the Greek letter
lambda.
Its SI unit is meter, m. Frequency tells us how frequently an event occurs. The change in density from the maximum value to the minimum value, again to the maximum value, makes one complete oscillation. The number of such oscillations per unit is the frequency of the sound wave. Frequency is usually represented by the Greek letter
mu.
Its SI unit is hertz. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. In other words, we can say that the time taken for one complete oscillation in the density of the medium is called the time period of the sound wave. Time period is represented by the symbol T. Its SI unit is second. Frequency and time period are related as follows.
Mu
Is equal to 1 upon T. The sounds made by violin and flute are different, though the fact remains that both the sound waves are traveling through the same medium, that is air. Both the sounds also travel with the same speed. Then why do we hear two different sounds? The reason being pitch. Higher the pitch, loud is the sound. Lower the pitch, soft is the sound produced. Remember, a low pitch sound has low frequency, and high pitch sound has high frequency. Timbre or quality of sound helps us to distinguish sounds. A sound of single frequency is called a tone. The sound which is produced due to a mixture of several frequencies is called a note and is pleasant to listen to. Did you know sound travels faster in liquids and non-porous solids than it does in air? It is also interesting to note that speed of sound increases with increase in temperature. For example, the speed of sound in air is 331 meters per second at 0 degrees centigrade and 344 meters per second at 22 degrees centigrade. Let us revise what we have learned. The waves are created by some form of a disturbance in a medium. A longitudinal wave is a wave in which the particles of the medium are displaced in a direction parallel to the direction of energy transport. A transfer wave is a wave in which the particles of the medium are displaced in a direction perpendicular to the direction of propagation. The amplitude of a wave refers to the maximum amount of displacement of a particle on the medium from its rest position. The wavelength of a wave is simply the length of one complete wave cycle. A wave has a repeating pattern. The wavelength is usually represented by Greek letter
lambda.
Its SI unit is meter. The change in density from the maximum value to the minimum value, again to the maximum value, makes one complete oscillation. Frequency is usually represented by the Greek letter
mu.
Its SI unit is hertz. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. Time period is represented by the symbol T. Its SI unit is second. A low pitch sound has low frequency and high pitch of sound has high frequency. Timbre or quality of sound helps us to distinguish sounds. That's it for now. See you in the next session. Here's a treat for your ears.